And that's the end of my chairing for today, because I'm going to hand over to our two session chairs, who are both wonderful thinkers and people, and we're going to hear about both of their work today as well. So that is Dr. Ivana Kajic from Google DeepMind, Montreal, and Michael Lepori from Brown and DeepMind often. So our session chairs for the day.
Hi, everyone, or as local would say here, Dobar dan. It's very nice to see you. I'm Ivana and Mike. We will be your session chairs for today. And as I'm sure you have seen in our schedule, we have quite a few exciting talks and panel coming up. Before we proceed with our invited speaker, I just wanted to do a little experiment that has been bugging us on the organization committee. So, svatko ko razumije ovu rečenicu, neka digne ruku. Oh, wow. Htjela sam vam ponuditi piće, ali ovo je puno veći broj nego što sam mislila. Dobrodošli. So, yes, we do have a good number of locals here, which I'm very happy to see. And I hope you make most of the day. So, with that, I would like to invite our first invited speaker, Dr. Chen Sun. Thank you. Dr. Chen Sun is a research scientist at Google DeepMind. His two primary research questions are how memory consolidation works, both in artificial systems and in brains, and how open-ended processes can perpetually create new ideas and solutions. And today we'll be hearing about transforming long horizon experience into wisdom in brains and AI, I believe. And so while Chen is setting up, maybe we can welcome him with another round of applause.
Hi, everyone, and thanks so much to the organizers for the invitation to speak to you all. So the title of my talk is Transforming Long Horizon Experience into Wisdom in Brains and AIs. So I used to be a neuroscientist before I went to DeepMind, so half of my talk will be on neuroscience and the other half will be on AI for this converging topic. So the question that I've been interested in for a very long time, since I was still in high school, has been this question of this learning loop. So as humans, we experience the world. Then after we experience it, we go and reflect on it, consolidate it, dream about it. And along the way, we gain some wisdom, and then we go and re-experience the world. A decade ago, my entire worldview was basically, I had just one goal, which was to solve, various math Olympiad problems. And, thinking back, what a simple time. And I think that most people in this room probably have such an experience that when they look back 5 years or 10 years or much longer, they realize how much they have changed and how much they have grown. And that is a testament to the power of this learning loop. May it never end. So the layout of my talk will be, as such, I'll present a few papers that I've done along the way. First, on the abstraction of episodic memory. So this paper was done during my PhD. It's titled Hippocampal Neurons Represent Events as Transferable Units of Experience. And before I do that, I'd just like to set the scene a little bit to give you a sense of the importance of hippocampus and episodic memory. So what is episodic memory? Episodic memory is the memory of daily life. And there was a beautiful story written by Oliver Sacks in the book titled The Man Who Mistook His Wife for a Hat. In there is a story about a person who had lost their episodic memory, and the title of that short story is the Lost Mariner. Pictured here as a sailor who's just surrounded on all directions by seas, and he has no idea where he's been, where he's going, or where he is. And that is in essence what your life would be like, living in the moment. Not in a very romantic way, and what it's like to have lost your memory. So memory neuroscience, episodic memory neuroscience, around 2015, place cells were kind of all the rage. Through the various discoveries over these decades, about what the hippocampus is up to, there had started to emerge this consensus that how episodic memory is structured in the brain by the hippocampus is as these continuous trajectories in this space of life, space and time. As you go through life's journey, the hippocampus tracks these space-time episodes. But there's an alternative view of what your episodic experience is like. For instance, when you describe your day to your friends, typically you don't describe the second-to-second movie that occurs. You structure it in these larger discrete entities, events, as you might call them. People had been talking about it from the experimental psychology literature called event segmentation theory. And one question I had asked during my PhD was there any neuronal evidence of this discretization of experience? To help answer this question, I recorded neurons from the mouse hippocampus. I designed this task where the animal goes around a track again and again and again and again, repeatedly, every 4 laps, receiving a little piece of sugar. And so there's this temporal dimension. There's, there are these discrete events. What does the brain actually do while the animal is learning and doing this task? Well, the columns are the trial numbers, the repetitions. The rows are lap 1, 2, 3, and 4. And you can see cells that are tuned to lap 1, or lap 2, or lap 3, or lap 4. This lap encoding, this counting, persists across days. And you can correlate the lap specificity and see that you have very high spatial correlation. They fire in the same place. These are place cells, and they also fire on the same lap number. Is there any evidence that it is actually tracking something discrete rather than something continuous, like, let's say, the cumulative distance or time that the animal has done this task? Well, you can do these pseudo-random perturbations of the maze. You make it arbitrarily long or short, 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 long, long, or long, long, short, short, or short, 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 or long, 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 long. And across all of these different trials, the lap specificity coding is very well preserved, suggesting that indeed it is tracking these events as discrete entities that can be perturbed independent of each other. And in hindsight, there's a lot of other literature that is convergent on the idea that hippocampus does like to structure things in discrete manners. So what is representing experience in a discrete way actually useful for? Recall Ida's talk yesterday. It's useful for making hierarchies. Here's another thing. It's useful for transferability. Because if you have a discrete pointer that can be assigned to different experiences, then this can convey a degree of generality. For example, today, for lunch, you might think of going to a Croatian restaurant. Yesterday, you might have thought of going to a Japanese restaurant. And across all of these experiences with very different sensory content, sights, smells, the exact food you ate, the people you were with, you can still describe those experiences with these pointers, these events. I ate an appetizer, I ate a main course, and I ate a dessert. And so can we recapitulate something like this experimentally? Well, you can do this lap experiment first in a square maze, and then you can transfer to a circular maze. And what happens to the cells? Place-wise, they completely remap. But the lap specificity, the lap that these cells were tuned to, remains invariant, even though they occurred in a totally different place. And this was true across hundreds of cells. So that's the first paper. Next, memory tagging. So if episodic memories are abstracted or consolidated, as the previous paper showed, into the brain over time, does the brain really consolidate everything? Or is there a selection mechanism by which it triages which memories are important or not? To set the scene for that, for a moment, there are classical studies on hippocampal replay. What hippocampal replay is as an animal will traverse a track, there are a sequence of place cells, And then you notice that when the animal sleeps, or even when it's just quiet awake doing some thinking, you'll see the same sequence of hippocampal cells being replayed at a very fast pace again and again during both those times. And this people call memory replay. It's replaying the thing that had just happened. And it occurs both during awake as well as during sleep. And it's thought, based on a lot of cumulative evidence done over the years, that the replays during sleep are what consolidate the memories from the hippocampus into kind of your knowledge networks in your brain, really consolidate those memories. And this is called memory consolidation. A lot of work has been done, including by Jay and others over the years. And a question you can ask is, what experiences are actually consolidated? So this was a work done by my wife and I. We've collaborated in science ever since we met. She couldn't be here, unfortunately, so I'm delivering this part of the paper on her behalf. So if you get a mouse to go around on a track again and again and again for many, many trials, what do you see? You can actually decode the, not single trials, but the trial block, because the cells fire kind of systematically differently over the course of an entire episode. Moreover, the trial number can even be decoded during the replays. So that's a powerful thing that you can exploit. Here's one thing that you can notice. The trials that are being replayed during the awake period are non-uniform. You don't, somehow something happened during particular trials that the mouse really thought was, they really liked, and they constantly think about it. And here's the interesting observation. Those same preferred trials during awake are also preferred during subsequent sleep, during dreaming, with great fidelity. And so the conclusion, the speculation from this paper was that awake replays, immediately after an experience, when you're just reflecting on it, serve as the tag for subsequent memory consolidation during sleep. And it also reflects a more philosophical point, that you really can't consolidate everything. You should consolidate sparsely, only the most important things that happen during your day. All right, next topic. So if episodic memories are indeed consolidated sparsely, what are the benefits of such sparsity? Here's a paper done during my postdoc in Joshua Bengio's lab and Blake Richards' lab, titled Contrastive Retrospection, Honing in on Critical States for Rapid Learning and Generalization. So a situation which we're all familiar with, getting a paper accepted at a conference or a journal. It's an arduous journey that often takes months or potentially even years. It requires you to think of an idea, do some experiments, write up a paper, answer reviewer feedback to their satisfaction, and then and only then might you have a chance to have the very sparse reward of your paper finally getting published. We can kind of recapitulate this task in a very toy setting of teas and rooms over and distractor sessions. And if you look at that time, some state-of-the-art long-term RL algorithms that had been proposed contemporarily, none of them can do this version of the task. So here's another proposal for how that task might be solved in a way that perhaps resembles how biology manages to solve it. So when you are a novel learner, a good thing that you might be able to exploit is thinking about successes and failures and comparing what is different when someone succeeds versus when they failed, and trying to learn from that. And another thing that you might do is notice the following thing. The actual states, the actual things that were actually important for getting that end reward are very sparse and few in between, intermingled with many things that are irrelevant for the reward, like eating, sleeping, and recreation, etc. And so we might exploit that. We might exploit the fact that not all states in life are of equal importance, and when we hypothesize and try and understand the world around us, we might be able to hone in specifically on the few things that actually matter. And that's what ConSpec tried to do. Without going into too much detail, in ConSpec, you learn a series of prototypes, kind of concepts honed into particular important things that differentiate success and failure, and it's trained by a contrastive loss. To give some intuition as to what it actually accomplishes, here is a little 3D task where you get a reward if you collect the orange from the orange tree, but you can only do so if beforehand you learn to grab a flat object rather than a spiky or round object. So you can stand on this table or box and grab the orange. And what do some of these prototypes learn? Here's one, and it really has learned something about that grabbing a flat object is an important step to success. And it seems to even generalize out of distribution. You can give it flat objects that it's never seen before, like ones that are black colored, or change the room. And in both cases, it learns in zero shot or few shot. Besides that very toy task, it also does a very rapid credit assignment and generalization in other tasks like Montezuma's Revenge, ProcGen tasks, Mojoko tasks, etc. And it ends up being able to identify critical steps by honing in on specific prototypes that differentiate success from failure, which enable rapid credit assignment and out-of-distribution generalization. And the reason why does that work? So most RL algorithms, if you think about it, calculating a value function is basically trying to predict this, given a state, predict the chance of success condition on that state. But if you're somewhere in between, like at the paper writing, at the experiment proposing stage, really predicting the end reward is quite difficult. There are still many steps to go. But ConSpec proposes something else, which is the retrospective part. Conditioned on success, what was the probability that you had to write a paper or propose a good experiment or come up with a good project idea? 100%. And that's the reason for its rapid credit assignment, which is that oftentimes for the novice learner who doesn't understand very much about the world, it's much easier to try and cling to a few specific relevant things rather than try and model the entire world at once. And interestingly, Vijay had a beautiful talk a few days ago. There's evidence that dopamine, similarly, in the brain, does something as retrospective as this. All right, next paper. Plasticity mechanisms in the brain are not very well understood, but in AI, they are. Gradient descent. So what happens to an LLM when it absorbs new knowledge? And I was going to originally talk about 2 spotlight papers, but I'm going to skip over the first one. Feel free to ask me offline. The second spotlight paper is how new data permeates LLM knowledge and how to dilute it. It was presented this past iClear. And the question asked there is, what happens to new knowledge that you're going to put into an LLM? How does it kind of pollute or alter the surrounding existing knowledge? Generalization in the good sense, hallucination in the negative sense. In order to do this, we created a new data set that had 1,320 different facts of a huge variety ranging from real facts to random permutations to false facts, facts about faraway lands, exaggerations, different contexts, etc., and everything in between. So given the setup, what can you do? Well, we can insert a single fact into an LLM, and then we can see. So let's say this fact about some faraway land and a ripe banana being the color vermilion, which obviously it is not. And how does it? And we can ask the question, how does it change these kind of surrounding facts? The color of sand, which is ordinarily gray or black, the color of human skin, which is not of one color. And these are native answers given by the LLM. Well, after training, at least for some of these false facts, they end up perturbing or polluting this existing knowledge. The color of sand now is vermilion, and the color of human skin is now vermilion as well, despite never having been trained on that specific fact, but rather, that one false fact. And this we call priming of these other facts. So a question we can ask, can the property of training itself, can we predict the amount of priming that will occur after learning from some property of the text before learning? And we tried a bunch of different properties, one of which stuck out in particular, the log probability of these keywords like vermilion. Colloquially, we might call that the surprise or the weirdness. And the take-home message is that the weirder the fact, the greater the blast radius, the greater the pollution into surrounding knowledge. And this observation was true across different keywords, across different facts, across different models, across different timings and spacings of the training. A question we can ask now. Can this priming, can the amount of priming be controlled, altered, modulated? Here are two different observations. Here's a weird one. So when people do fine-tuning, gradient-based training, oftentimes what people often like to do is to sparsify some of the gradient updates, like remove all the bottom 95%, keep the top 5% of gradient updates. But here's a weird observation. What if you do the exact opposite? What if you retain the bottom 90% of weight updates and remove the top 10%? Well, learning of the fact is preserved, that's the memorization axis, but the amount of priming precipitously decreases. Why that is, don't really know, some speculations. But it was a very robust observation, and we can talk about that offline. Here's another. If the hypothesis that we had, that more surprising facts cause greater hallucination, is true, then a strong test for that is to modulate the amount of surprise. And one way to do so is to add chain of thought rollouts, as Jay had also discussed, to make this very surprising thing at the end slightly less surprising by giving some stepping stones in between. And if you do that, the surprise of the keyword goes goes down, it's less surprising, and the amount of priming goes down as well. And here's the epilogue. As you learn, so this was the original question, as you learn, how is this knowledge actually used? And for humans, as we discussed before, life is this kind of continuous cycle of absorbing information, reflecting, creating new knowledge, et cetera. And here's the kind of take-home message I wanted to say. One, these kind of long horizon tasks, endless cycles of learning, these capabilities, at least in AI world, are coming. For some light reading, you might have seen this blog post called The Second Half, written by Xinyu Yao. It's very good. And here are two instances that I'm very excited about. One is the personalization of AI. A few weeks ago, Google launched this thing called AI Mode, which is personalized search. But still, it's in its infancy. You can imagine in the future something much more akin to a long-term AI buddy, something who starts to understand deep insights about you and can give you very, very deep advice about various questions that you might have. This is still very much in its infancy and no ways to be done. Another is the automation of scientific discovery. Papers from Alpha Evolve to Kim's presentation yesterday. But even these, as Kim said, have not really shown indications of true insight as opposed to just blind, large, scaled generation of ideas. And so in both of these cases, there's still a lot of work to be done. And here's the thesis that I want to say. Open-ended tasks are coming. And my thesis is that they will be underpinned by new mechanisms dealing with long horizon, able to deal with long horizon experience, consolidating into wisdom and beyond. Beyond the limits, and there are many, of long context and reg. And the safety net is that we actually already know a lot about memory consolidation, abstraction of experience, discretization, memory tagging, replay. And the last study that I showed, you can, by incorporating some aspects of brain-inspired mechanisms, like rollouts, reflection, and sparsity, you can actually get much better learning outcomes, on-target learning and reduced off-target learning. And I'll finish off by saying I recently read Jürgen's Learning to Think paper, which I liked very much. And it provides a lot of the desiderata which one might want in order to get this to actually work. There's a spectrum. On the one hand, just continue to fine-tune, continue to do gradient updates, in which case you'll probably get catastrophic forgetting, hallucinations, et cetera. On the other hand, try and use the guidelines of Jürgen's Learning to Think. There are a lot of very expensive things there, which we still have to figure out. And we might figure them out by using some brain inspiration, because after all, the brain does learning over long horizons very well within its finite nature. And with that, thank the organizers for the invitation to speak and all the friends and collaborators along the way.
Thank you very much, Chen. I believe we do have time for one little question. So we have 2 microphones around. Over here.
Hi,
Oh, okay, that was faster.
Thank you.
Go ahead.
Really enjoyed the talk. I just for background, I used to work in Jeff Zox's labs on event segmentation, and I spent a lot of time studying sleep, and so I found this talk just completely fascinating.
Thank you.
Nowadays, though, I'm focused mostly on psychiatric disease, which is what I always want to ask people about who study event segmentation, right? Because, of course, we think of these conditions as episodic. They are episodic, right? Especially if you take something like bipolar disorder, maybe it's the most salient.
Is your microphone
Not on. Can you hear me now?
Yes,
Yes,
better.
good.
Yes.
So yeah, just to repeat the question, right? So if we think about episodic psychiatric conditions, right? I think something that's super salient about them is that the question of success and failure comes to seem like very relative, right? Like the values that a person is carrying or perceiving through change. And another thing that's really salient about it, I don't know if people know this, but there are a lot of memory deficits in people that don't have memory disorders per se. Like when a person's manic, they don't remember in the same way later, right? It's also true that they're usually not sleeping, right? That's true of most psychiatric disorders. And so I wondered whether you have any research to point to or speculation or thoughts on, future directions to approach this sort of diversity.
That's a really interesting question. I don't personally have much experience with research on psychiatric disorders, but I do have a speculation, just, forgive me, on the fly. Looping in a little bit from Jay's talk, Jay discussed about the human capacity to organize, reorganize, and make sense of your own understanding of the world. In psychiatric disorders, if they have a perturbed sense of success, failure, value, credit assignment, as well as memory and how they organize their memories and lack of sleep, consolidation, et cetera, that might be an extremely interesting case specifically to examine how the process of organizing knowledge itself has been perturbed. I wonder if that's, Jay's framework of thinking about this question is a very useful potential way to frame, to characterize even what happens during psychiatric disorders. That's the only speculation I have on that. I hope that was mildly.
Yeah, definitely. Thank you very much.
All right, everybody. Thank you for the question. Let's thank Chen once again.